This is a production of Cornell University.
Giving you sort of a fairly good sort of a cartoon of the scenario. Soil surface up there down to 120 centimeters, basically soil depth, okay? And this is basically oxygen. The more that you go that way, the more oxygen's in the system. The two lines represent rain events, or before a rain event and after a rain event. The first line here is before a rain event. The second line here is after a rain event. Well, this goes back to what your comment was. Well, you know, if water is moving into this system, air is going to be driven out. Forget about the respiration. Just look at the mass flow. Before the heavy rain, oxygen content down to 120 centimeters is about 15%. You get farther up and you get closer to the surface and increases dramatically. Okay? After that rain event, the oxygen is just basically driven out. And this has nothing to do with respiration. This is just mass flow. Make sense? So let's take this a little bit differently. Instead of looking at the oxygen content, let's actually look at the CO2 content. Now, why would I look at the CO2 content? The CO2 is a representation of respiration, of aerobic respiration. Okay, if I'm breathing oxygen, I'm going to be respiring CO2. Okay, so if I look at CO2 concentrations, it gives me a measure of how much respiration is going on. If I look at O2, it doesn't actually tell me how much respiration is going on. It just tells me that there's the potential for respiration. Does that make sense? I look at CO2 to tell me that, in fact, respiration is going on. Okay, so let's look at CO2. This is CO2 concentration. The assumption is the more CO2 concentration you have, the more respiration you have. And then this is depth. Okay, so looking at 0 down to 800 centimeters. Okay, so 8 meters down. Okay, now let's look at a seasonal issue here. We're looking at a dry season versus a wet season. Dry season. Lots of pores. They're not packed with water. I should have lots of gas exchange. My CO2 level is down, though. Wet season, CO2 levels go up. What's happening in this scenario? This is not a case of water moving into the system and driving everything out. Because if the water is moving into the system, like this scenario, my CO2 levels would basically do the same thing, because CO2 is in the gas, right? Does that make sense? In this scenario, something else is happening. Oops, wrong way. What's happening? System starts getting wet. What am I going to start seeing happen? This is a dry system, no water at all. If I don't have any water at all, I'm not going to have any biological activity. System starts getting wet. I start seeing an increase in biological activity, and so as a result, I see an increase in the concentrations of CO2. Okay, so we have a seasonal issue where we're actually seeing increases in respiration. We have a seasonal event where we see basically mass flow of stuff moving out of the system. Go.
How do you distinguish the increase in CO2 from respiration from an increase in CO2 that might occur from less gas exchange? Like it's building up.
It's building up, right. So the question is, how would I see the difference between respiration CO2 being involved versus just a buildup of CO2 with less exchange? Good question. I mean, my answer to that, and I do not know if this is actually the instrumentation, how we would do this instrumentation-wise, but my answer to that would be, well, if I'm seeing an increase in the relative CO2 concentration, it doesn't matter whether I have less oxygen in the system or less atmosphere in the system or more atmosphere. The relative concentration of CO2 in that total atmosphere represents that respiration. Okay, so if I have a dry soil, and say it's dry and they still are respiring, okay, granted that's probably not going to be the case, I'm going to have a certain fraction of CO2 in that soil. Okay, now if I reduce that because I put more water in, the relative concentrations between O2 and CO2 are still going to be the same. There's just going to be less of both of them. Does that make sense? Does that make sense to everybody? So the question is really, how do I differentiate between what CO2 is being evolved from respiration? Okay, so if I'm looking at an absolute concentration, This is a percent versus an absolute concentration. So if I was saying that, there's X amount of CO2, I would really want to know what that X amount percentage-wise is with all of the soil. Okay, because then that percentage should stay fairly constant with respiration. It doesn't matter how much actually gas I have in that system. Does that make sense to everybody? Questions on that? Go.
If it's if the soil's sealed off by water, then no more O2 can get in. Then the CO2 concentration is going to rise.
Right.
In proportion to the O2.
Correct. And that's sort of that measure of CO2, though. But if it does rise, it's telling me that there's respiration.
Right, but if the same soil is not sealed off by water and it's getting in oxygen, wouldn't the CO2 concentration be different, even though there'd be the same amounts of respiration?
Okay, so we take a system where it's not sealed off, and we look at CO2 evolution. And then we seal off this, and so the relative concentration of CO2 should increase relative to everything else.
Right.
Okay, but yes, and so I've got a measure of 2 times. Now, how do I compare those two systems to each other? I basically look at the total amount. So I got a system that's got some sort of seal at the top. Okay, so no exchange is happening. Now, the reality, that's not going to be the case, but there's going to be slower exchange, but at least with Earth systems, versus a system where there's no barrier. Okay, so you should see a percentage of this being CO2 versus O2, and that's your percentage. Okay, in this scenario with respiration, this CO2 percentage should increase to oxygen because there's no oxygen coming into the system, but there's a buildup of CO2. So how would I tell the difference of respiration in these two scenarios? Well, in this scenario, I tell the difference in respiration because I've got this fraction up here. I've got a CO2, O2 fraction up here. Okay. In this scenario, I basically base it on what's happening in a time. I look at it as in a temporal scale, or what's happening over time. And so time 0, this should be like this. And time n, whatever it happens to be, the line should be here. Does that make sense? And does that make sense to everybody else? It's actually, this is a pretty important, I mean, it's well beyond what we're supposed to be talking about today, but it's a pretty important concept because there's a lot of people that are doing research to sort of understand what's going on down here. This is just a measure of activity. It doesn't actually measure what they're doing. This could be one really large organism, or it could be the millions of organisms that we generally think of that are in that soil surface. Okay, so this is just a measure of activity, but it gives us an idea about what's going on in this whole volume of material we call soil. Go.
So, if it means that there is more carbon dioxide at the deeper levels, does it mean biological activity is more down than the shallow regions?
That's actually a good point. Okay, if I have more CO2 down here than up here, does that mean that there's more biological activity down here than up there? No, what it really means is there's more exchange. The exchange of oxygen is faster up there than down here. For that CO2 to exchange and oxygen to replace it, it has to travel 700 centimeters. For it to exchange up there, it only has to travel 100 centimeters. And that's what's happening. And you also have to imagine with all the organic matter basically being concentrated at the surface, this line is actually skewed because, in fact, there's a lot more respiration going on up there than down here. Okay, we good? This is a seasonal. I just sort of, at this point, I think we're beating a dead horse, but here's June. This is basically looking at the growing season, and you're looking at that soil depth, and you're looking at concentrations of CO2. So this is seasonal CO2 content in an alpha soil in Missouri. Okay, and here's depth. And you're basically looking at lower concentrations of CO2 up there than here. But what's really the important story here is as the growing season progresses, you start getting into June and August where you have a lot of photosynthesis, you have a lot of biomass accumulation, a lot of respiration going on. Okay? And you can look at the CO2 concentration dramatically increase. And it increases all through the profile. Okay? Sooner or later, we're going to start seeing senescence and biological temperatures are going to start coming down. Biological activity is going to be reduced. And so as a result, we start seeing it coming back to fairly similar to what it was in June. Okay, we're looking at what happens at biological activity during the biologically most active time of the year, at least in the northern hemisphere. Does that make sense? This is just sort of a reiterate the question. All right. So I think we made the point at this point, hopefully. We've made the point that saturated soils have little or no air in their pores as the system gets wetter and as respiration happens. Okay, so it's not just the water moving in and driving the oxygen out. It's also the water moving in and the oxygen being driven out and the oxygen being used up for respiration. Okay? Now, saturation can be temporary or in fact could be permanent. A temporary situation is a rainstorm where you come into some sort of permanent, some sort of impermeable barrier, water hits that and then slides sideways. Good example was what you guys saw at the Mardens. These are those frangipans. Here's those funnels. You know, the water comes down, hits those frangipans and stalls. Yes, you have some drainage this way, but you see an increase in the water table here, but that water table ultimately is going to slide off and your system will go aerobic again. Another example of this, though, this is not another example. This is a different example, a permanent water table, where you're basically looking at the water table coming up and holding there. So this is a permanent. So below this, it's anaerobic. Above this, it's dry, aerobic. Good example of this is when we're up at Mount Pleasant as well. Remember we did that boring? Okay, and we did that boring down at the bottom. Okay, the first soils that we brought up were nice and brown. They had lots of red features, lots of redox features, redoxomorphic features modeling. Okay, but as we went farther and farther down, that red started to disappear. And then you started seeing it just along the root channels, and it became really gray with just red where the root channels were. And that oxygen's not coming from the ground. That oxygen is being pumped down by the plants. Okay? That's a good example of where you're basically at this interface. Above it, you've got oxygen. Below it, that's where you saw those big, bright red models. Yeah, there's a period of time that that's saturated, but it comes back down. Below that, that's where you go into those grays, permanent grays. Okay? You can hold up on that.
This has been a production of Cornell University. On the web at cornell.edu.